Welcome to the Explainer. So, today we are decoding the mathematics of motion, and honestly, we're going to unpack a concept that trips up almost everyone at some point. I call it the speed trap. We're going to figure out the hidden, and honestly completely counterintuitive rules of velocity and acceleration. Let's get right into it. Okay, let's dive into this. Here's a question for you. Does positive acceleration always mean you're speeding up? I mean, instinctively, you'd probably scream, "Yes! Step on the gas!" Right? But in the exact world of physics, assuming that is actually a massive trap. To understand why positive acceleration can literally mean you're slamming on the brakes, we kind of need to completely rewire how we think about motion. You see, the whole trap stems from blurring the line between speed and velocity. Speed is just the magnitude, like 50 kilometers per hour. But velocity brings direction into the math. So moving 50 kilometers per hour to the right might be a velocity of plus 50, but moving at that exact same speed to the left gives us a velocity of minus 50. The physical speed is identical, but the velocity is totally different, all because of that vital plus or minus sign. To really get a grip on velocity, we first have to establish the ground floor, which is position. In physics, we usually label this with an S. It's basically an object's location relative to a starting point, but here's the crucial part. It relies on a specifically chosen positive direction. If we decide moving right is positive, then a position of positive 20 means you're 20 miles to the right. A position of negative 20, you're 20 miles to the left. Everything, and I mean everything, hinges on which way we decide to point that positive arrow. And it's crazy because this simple choice of direction changes the whole shebang. Let's say a car is moving from point A to point B at 4 miles per hour. If we make point A our zero, our start line, the car's distance from A is growing, right? So its velocity is positive 4. But what if we measure from point B instead? As the car drives, its distance to point B is actually shrinking. So mathematically, its velocity is negative 4. The car didn't suddenly throw itself into reverse, we just changed our coordinate system. The physical reality stayed the exact same, but the numbers flipped, simply based on our perspective. So how do we link these pieces, position, velocity, and acceleration, together? Well, think of it like a tree with 3 branches, just stepping down through calculus. Step 1 is our position, S. If we want to know how fast that position is changing over time, we take the first derivative, which gives us step 2, velocity. And if we want to know how fast velocity itself is changing, we differentiate one more time. That second derivative of position gets us to step 3, acceleration. So position goes to velocity, and velocity goes to acceleration. Now, here is where we hit the core myth, and you really have to wrap your head around this. Increasing velocity does not always mean increasing speed. I know, it sounds completely backwards. In everyday conversation, those two phrases mean the exact same thing. But in physics, blurring that line is exactly what springs the speed trap. Let's just look at the math to prove it. Imagine an object's velocity changes from -8 to -5. Mathematically speaking, on a standard number line, -5 is further to the right than -8. So -5 is actually the larger number. The velocity has mathematically increased. But remember our earlier distinction? Speed is the absolute value of velocity. The absolute value of -8 is 8. The absolute value of -5 is 5. So the physical speed went from 8 down to 5. The velocity increased algebraically, but the actual physical object slowed down. Crazy, right? When you map out the math, there are really only 4 combinations for the signs of velocity and acceleration. If both velocity and acceleration are positive, you're moving forward and speeding up. Simple enough. But if they fight each other, like positive velocity and negative acceleration, you're moving forward but slowing down. Now, what if you're moving backward with a negative velocity? Well, if acceleration is also negative, those negative velocity numbers are getting bigger in magnitude, say going from -2 to -8, meaning you are actually speeding up. But honestly, you don't need to memorize a complex matrix. It all boils down to one super simple memory trick. Same signs mean speeding up, and opposite signs mean slowing down. It is that beautifully simple. If velocity and acceleration are both positive or both negative, the object is getting faster. If one is positive and the other is negative, they're fighting each other, and the object is slowing down. Why? Because again, speed is just the absolute value of velocity. All right, let's take this out of the abstract and put it into the real world. Imagine taking a ball and throwing it straight up into the air at 96 feet per second. To keep things perfectly clear here, we're going to explicitly declare that up is our positive direction. Let's see what happens to the math. The split second that ball leaves our hand, the math totally takes over. Our position equation is 96t minus 16t squared. Following our derivative tree, we differentiate that once to get velocity, which gives us 96 minus 32t. Differentiate velocity again, and we get a constant acceleration of negative 32. Now, why is acceleration negative here? Simply because we chose up as positive, and gravity is constantly pulling down. Gravity is fighting our positive direction, hence the negative sign. So, let's test our rule. At the exact moment of launch, time is 0, our velocity is positive 96, and acceleration is negative 32. 1 second later, our velocity drops to positive 64, while acceleration remains negative 32. Notice the signs here. We have a positive velocity and a negative acceleration. Opposite signs, which perfectly predicts that the ball is moving in the positive direction, upward, but it's slowing down as gravity fights it. The ball just keeps traveling upward, getting slower and slower, until it reaches exactly 3 seconds. And at that exact instant, at the absolute peak of its trajectory, the ball just freezes in midair. Its velocity hits exactly 0. Now, what's really interesting about this slide is a massive misconception people have. 0 velocity does not mean 0 acceleration. Even when that ball is frozen for a split second at its peak, with a velocity of 0, gravity hasn't taken a break. The acceleration is still negative 32. The ball is continually accelerating downward, which is exactly why it doesn't just float there forever. If we trace the ball's complete chronological journey, you can see how our rule of signs perfectly predicts its behavior at every single stage of the flight. Going up, velocity is positive, acceleration is negative, opposite signs, so it slows down. At the top, velocity is 0, but acceleration remains negative. Then, as it falls, velocity becomes negative. Acceleration is still negative. Because both signs are negative, meaning they're the same sign, what happens? It speeds up as it plummets back to Earth. But what if we change things up? What if we were throwing the ball down from a roof and we decided to call down our positive direction? Well, in that coordinate system, gravity is pulling in the positive direction. So gravity's acceleration becomes positive 32. The physical force of gravity didn't change at all, right? We just flipped our perspective. The math beautifully adjusts to reflect whatever coordinate system we choose to overlay on the physical world. Ultimately, this whole explainer really boils down to 3 foundational questions that define the fundamental physics of motion. First, where is the object? That's our position. Second, how is its position changing? That's our velocity, the first derivative. And finally, how is its velocity changing? That's our acceleration, the second derivative. If you understand how these 3 link together, you have completely decoded the math of motion. Which brings us right back to our opening hook. If acceleration is positive, are you speeding up? Well, you now know the answer. Only if the velocity is positive too. But here's something to chew on before we go. Everything we've discussed today assumes motion in a straight, one-dimensional line. What happens to the math when you introduce a curve, or a second dimension, like a car drifting around a corner? Do these rules of signs still hold up? Well, I'll leave that for you to ponder. Thanks for joining me on this explainer, and I'll catch you next time.